Hello, calculus students. Today we are going to take notes on section 4.2, which is the Rolle's theorem and the mean value theorem. Let's start with folding our notes. You're just going to fold the notes right in half, and then you're going to cut along where I drew an orange dotted line. So it'll be like a little booklet where the top opens up and the bottom opens up. Next, let's start with an investigation. Let's think about plotting 2 points on a graph. So I'm going to just draw a sketch and plot any 2 points. Go ahead and connect those 2 points in any smooth curve, however you want. Now, next, I'd like you to find the slope of the secant between your 2 endpoints. So I connect my 2 endpoints, and I can find the slope, m, of my secant. I know it's going to be negative, and I'm just kind of guesstimating here. Let's say this was about -1/2. Then, what you want to do is find any other points on the curve that would have the same slope as the secant line that we just drew. And so imagine a tangent line coming along the curve like this, and it's coming along. And eventually, we're going to find a point where the slope is the same as the secant. There's probably another one up here. And this always happens. So that brings us to Rolle's theorem. If our function is continuous and closed from a to b, and it's differentiable, and if the function value of a equals the function value of b, then there's going to be at least one number c such that the derivative equals 0. Now, it might seem a little confusing because in Rolle's theorem, in their investigation, they are making points a and b exactly the same values. So let's say I did something like this. There's point A and B, and the slope between A and B would definitely be 0. So what Rolle's theorem says, there's going to be at least one other point where we also have 0. There's going to be a derivative equal to 0. When we had this angled one that we first investigated with, that is going to be giving us the mean value theorem. So let's try a Rolle's example. Again, Rolle's theorem says that there will definitely be a derivative equal to 0 at some point between the 2 x-intercepts, let's say. So let's first find the 2 x-intercepts of this function. That means we need to equal this to 0. It's a quadratic, so I'm going to factor it and get my 2 x-intercepts of 2 and 1. So I know my graph crosses at 1 and 2, happy face graph, okay? So what we now want to show is the first derivative equaling to 0. So let's find our first derivative. We get 2x minus 3. When I equal that to 0, I get x is 3/2. Notice that 3/2 is between 1 and 2. So we just proved that between the x-intercepts 1 and 2, we have another location where the derivative is equal to 0. And it's between those 2 x-intercepts. Let's look at the mean value theorem. It's very similar, but we don't have to be equal to 0. We could be equal to whatever the secant slope is. So if f is continuous on a closed interval a to b and differentiable on the open interval a to b, then there exists a number c in the interval a to b such that the derivative of c equals f of b minus f of a over b minus a. In shortcut, this is saying the derivative at c is equal to the slope of the secant from a to b. Okay. In words, we are looking at the change in y over the change in x, or the slope of the secant line. So this looks like fancy notation, but you're just figuring out slope, y2 minus y1 over x2 minus x1. The mean in the mean value theorem refers to the average rate of change of the interval a to b, of the interval from a to b. The mean value theorem guarantees the existence of a tangent line that is parallel to the secant line through the points A, f of A, and B, f of B. So how can we complete this mean value theorem? The first thing you want to do is ask yourself, is the function continuous on the closed interval and differentiable? Because if it's not, then we're not even going to be able to prove the mean value theorem. Step 2. By the way, step 1 is just going to be a yes or no question. If it's yes, continue. If it's no, you can stop. Step 2, we need to find the slope of the secant line through the endpoints. I'll call this m secant. Then we need to find the derivative of the function. That's f prime of x. Step 4, we need to set the derivative equal to the slope of the secant. So we do m secant, which you calculate y2 minus y1 over x2 minus x1, set that equal to the derivative, and then you're going to solve that. So you'll find all the points, x, y, in the interval where this would be true. So we're proving the mean value theorem by showing there are points in the interval that the slope of the secant equals the derivative. So let's try an example. We're given the function 5 minus 4 over x. We want to find all the values between 1 and 4 such that, and they tell you exactly right here what we're doing. We're doing the derivative of c, where it equals the slope between 1 and 4, the two endpoints. So first, is the function continuous on the closed interval from 1 to 4? You can graph the function and look at the graph and realize that yes, this will be a continuous curve and it will be differentiable on the interval. So let's find the slope of the secant through the endpoints. You can do it in function notation, like the book probably shows you, or a WebAssign will show you, or just keep it simple. The x values are 1 and 4. Plug 1 into the original function and get a y coordinate of 1. Plug 4 in and get a y coordinate of 4. So y2 minus y1 over x2 minus x1. We get 3 over 3, or the slope of the secant is 1. Step 2, or 3, find the derivative. The derivative of this function, you may want to rewrite it as 5 minus 4 x to the negative 1. The derivative of 5 is 0. Power rule for the next term will give us 4 x to the negative 2, or 4 over x squared. So now we're going to use the mean value theorem by setting the derivative equal to the slope of the secant and solving this. I'm going to make it a proportion and cross multiply, square both sides, and you will get positive or negative 2, but keep in mind our interval is 1 to 4, so I'm only going to use the positive root. So the point is 2, it should not say yd, it should say xy. 2, and that's where it's happening at. You could plug 2 into the original function and get 3. So the point 2, 3 will have the same slope of the secant.